So after the break, I will sometimes show you some useful tips and tricks that don't fit otherwise into the lecture, and I think that might be useful for you to learn. Anyway, so the first tip of the week, I call them tip of the week. The first tip of the week is a special file that you can add to your Git repositories to tell Git to ignore specific types of files. And the reason is that if you have a bit more complex Git repository, often you end up having files in there that you don't necessarily want to track. So for instance, if you have Python files in there and you run the Python file, the Python interpreter will create semi-binary versions of that Python file called PYB or PYC that you don't, well, actually this is a compiled one. Anyways, that you don't want to have in your repository because they are just kind of caching files that Python creates. And it becomes a bit annoying because if you ask for Git status to know what files you've changed, then you potentially end up with a long list of files that you're not interested in knowing the status of. And so the way you can get around that is that you create in the root folder of your Git repository, you create a new file called .gitignore. And in that file, you simply list all the files or file types that you would like to ignore. So for instance here, if I want to get rid of all this .cache and the .pyc files, I would have a gitignore with 2 lines. The first one with the content .cache and the second line star.pyc. And then you add that .ignore. You typically add that .gitignore to your Git repository and check it in as well. You don't need to, but it's good practice because then if you download that, clone that repository on another computer, you automatically ignore the unimportant files as well. So you typically do a git.gitignore and then commit it. So yeah, just here's an example how that gitignore file might look like. So for every line you specify the types of files that you're not interested in. And then if you do another, now I've added it and I do another git status, and you'll see there's, now my git status is very clean. Does it make sense? Hope it's useful. Okay, but we had been back to Bash. We had been talking about piping or connecting commands together. And I've shown you this example on how we can select all the files that are, all the Jupyter files in my lecture folder. Just to give you another example, here's another useful command that you're going to learn in the meantime. It's called man. The man command shows the manual of a Unix bash command. So if I'm interested in which options, or what does the grep command do in Unix, I can type man grep. If I execute it, I get a very detailed overview of what grep does. Right? It print lines that match patterns. And then it's, I mean, this is very long, right? And so if you're interested in a specific, I mean, I don't want to read all of this just to figure out how I want to do a certain thing. So let's assume I'm interested in only, I want to know the option that does the filtering case insensitive or sensitive, right? So sometimes maybe I don't care if they're capital letters or not. So I just want to tell grep, please filter lines with but don't care about the case of the letters. So then what I do is I take this manual page and I redirect that output again to grep because I use grep to to filter its own manual page, and I'm only interested in lines that contain the word case. And so if I do that, very useful, it immediately pops up with -i or -- ignore case. So that command line option makes grep to ignore case distinctions. Okay? So that's it. So I didn't have to read the entire manual page to figure out that command line option. So now back to our Oslo weather forecast. I'm going to do live programming to hopefully we'll recreate the script that I showed at the beginning, but I just want to show you the progress on how this is done, just so you get the typical work pattern when you create these pipes. So again, the task was we want to display today's weather forecast in Oslo. So the first thing that I do is I need to get the information from somewhere. So I go to yr.no. Then we're interested in Oslo. Okay, let's go to Oslo. And okay, this is the page that contains the information that we want, right? So I want to get essentially the temperature up here. So then what I do is I copy the URL here, and I go to my shell. And let's do this. And so now I use curl. So curl is the program for downloading web pages. So I type in curl and the URL. And if I execute this, right, you get a lot of text. And that's essentially the website as HTML. So that's the language of the websites with all the information that we're interested in. So of course this is way too much. So now the task is to kind of reduce it to the information that to only the temperature. So how do we do that? Well, we need to, I assume now that the temperature will be somewhere in a line in that file. So and the easiest way to figure out which line that is to use grep. And I know that there's going to be somewhere this 20 degree in that long output. So what I'm going to do is I use this pipe symbol and then grep, and then I just grep for 20. Let's see what we get there. Okay, that's still way too much. So maybe let's try 20 degree. That's much better. So let me just show you this again. So I now grep for 20 degree. So now I filtered only lines that contain the 20 degrees here. And so now you can already see we are down to 2 lines, right? So that's good. But of course, it's a bit useless because tomorrow it might be 21 degrees, and then the script won't work anymore. So I need to find a better way to characterize these lines. And one thing that doesn't change is this word temperature here. It turns out this always pops up. So instead now of searching for 20 degrees, I change it to filter only lines that contain the word temperature. So now we get a few more. And you can already see that now we get all the temperatures also for future dates. Right? So that's quite useful. We start getting the right information that we're interested in. So, we don't want to get the temperatures of all the future ones. We're only interested in the temperature right now. So now I want to limit that output to only the very first line and just discard all the rest. To limit output, we have another command in bash, and that's called head. Head takes in the input and then limits the output, and I can specify how many lines I want. So I just say I'm only interested in the first line. So that did not work as expected. Sorry, let head minus n equals 1. Okay, let's clearly have doing something incorrect. It's the problem with live demoing live. Oh, I have a double pipe. That's why. There's 2. Okay. So now I restricted it to the first line only, which is good. But now, of course, I'm only interested, I don't want to have all this HTML commands. I'm only interested essentially in the title. So I'm only interested in this part here. So how do I do that? I interpret this line here as a table that is separated by these double colons. And then I select the relevant column that represents that text that I'm interested in. So the way this is done in Bash is, and so now, of course, I've forgotten the command. Does anyone know? Okay, we need to look it up. Oh, I have it. Cut, thanks. Cut, and then I need to specify the delimiter, and I need to use the back colon to specify the double colon. It's just a technical detail. And okay, let's look at the manual page of cut. So D specifies the delimiter, and then I want to say which column I'm interested in. And that should be F. So let's just try -F. Let's take the first column. And you can now see that I get the first part all the way up to the first double colon, which is, of course, not what I want. So let's count. The second part should be temperature plus. It's correct. The third part should be this title thing that I'm also not interested. I'm interested in the fourth column. So now let's just clear this for a second again, the screen. And let's try our final command. So we have, first we get the web page, then we grab the lines with the relevant words inside, then we restrict these lines to only the first one, and then we interpret as a table and cut the fourth column of it. And that's the string, and then if you want, you can have this cowsay at the end to print this text as a nice cow output. Okay, so you can see that you don't come up with these scripts at once, right? There's a kind of an iterative process that guides you to it. But you need to be aware of these kind of little programs like curl and head and so on that allows you to operate on that text. So just another example, because I think it's so important. Let's say your task is to sort out, it's quite a common situation, right? Your hard drive is full and you're supposed to kind of find the largest file so that you can tidy up a little bit. So essentially my lecture files was way too big. I needed to get rid of some files. So what I did is I sorted all files in this directory to lectures, and in such a way that the largest files appear first. And then because there's so many files, they would just fill up my entire screen. I use a paging functionality so that I can scroll up and down on the screen. So less provides that. So okay, the way you do that is disk usage shows the file usage of every single file. It does it recursively. That's why I have the -a here, and this is the folder that I'm interested in. Then I use the sort command to sort the lines in a reverse mode and numerical. It's just these options that you can look up. And then I pipe that output to the less command, which gives me a nice paging. So if you want, we can test this also. Let's go documents UI over here. I think this should work. So if I run this, I just copy and pasted it, and this is the output. And okay, so the first ones are just the overall folders that, of course, very big. But then here are the interesting files. So these, I have some CSV files that are fairly large. And then this is here given in bytes here. This is the size. You can see the size reduces. And then the less command that allows me, if I use my keys, up and down keys, I can go up and down in the output. This is the pagination, essentially, of less. Does it make sense? Okay, here's one more example that in another command really that's often quite useful. It's called the T command, and that what that does is it is essentially, well, it's called here you can see why it's called T. So you take one, you have the output of one command, and if you pipe it through T, then the standard output will be duplicated. It once goes into it comes out as a standard output, so you can pipe it again to a less, but it's at the same time written to file. So why this is quite important is because when I compile my models, for instance, or if I run simulations, I often want to see the results on screen, but at the same time I also want to store them on file, just in case I want to look it up later on. So it's this T command that you want to use in these cases. And so then, of course, right, I told you about redirects, where you change the path of the streams and pipes, but of course you can also combine them. So in this example, I have a compiled script. I want to redirect the error stream into the standard output stream. So now everything is just standard output. That standard output is passed to T, which then saves the standard output to file, but it also passes it on to less, and in less I can then paginate through it and look through the output. So here's a simple quiz again. The following command, and yeah, there's this double N, so it explains here what it does. So can you figure out if we can write this command more elegantly, or this line? Or can you maybe figure out what it does in the first place? So this double end simply says we first execute one command before, and then if that was successful, then we execute another command. I could have just written 2 lines, doesn't matter. But so what do? We use ls to list the files in my current directory, and I store that list in a text file, right? And then my second command is I use grep, so I filter files, and I'm only filtering files that have the word 2017. And as an input file, as a standard input, I use files.txt. Okay? So what I do is I take the output of ls, store it as a file, and then I use that file as an input to grep. So that's essentially we've coupled 2 programs. We've coupled the output of ls and used as an input to grep. So instead of doing that by storing the results in a text file, we could have also just used the pipe straight away, right? So we could have just written ls : grep 2017. And so of course, there's a difference here that the text file isn't created, so maybe you need to use T in addition if you also wanted to create the text file. But do you see does it make sense that they're, at least from the idea that they're doing the same things? Yeah? Okay. So then I'll show you some some more syntax embeds that you can use. So there's if statements. So this is an if statement that compares two strings. And here's another syntax that you need to be careful of. So when you have these conditions in the if statement, use the curly bracket and a semicolon at the end, and there must be spaces here. So remember to always add spaces before you add the condition. And by default, this double equal sign here does a string comparison. So sometimes you might have not strings, but integers, right? If you've declared the type. And if you want to do an integer comparison, you can use this -eq to do an equality check. You can also use -gt for greater than or lt for less than. But otherwise, the if condition looks the same. There's just one thing that you need to be careful with. The problem, so this example here, where you do an integer comparison, you need to be certain that the variable here is actually an integer, because otherwise you end up comparing a string to an integer, which is going to give surprising results. So unless you're absolutely certain that this variable is an integer, it's actually better to always do a string comparison. So the way you convert a variable to string is to simply add double colons. Right? So for instance, here's the special variable $?. Right? It gives tells you if the last command was executed successful or not. So I'm not sure if this is a the value of this can either be 0 or 1, depending if the command was successful or not. But I'm not entirely sure if that variable here was declared as a integer or not. It's a magic variable. So to be able to do a safe comparison, I convert the variable to string, and then also use the string comparison here in the if statement. So the last one, or minus not equal here, might not be a safe choice to do. Yeah?
We cannot use double equal for integers.
Okay, so the question is, can you use double equal for integer comparisons? And I'm actually not sure. Does anyone else know? No. I'm not certain, but I typically tend to use these minus equal just to make it clear that this is an integer comparison rather than a string comparison. So another very important part of Bash programming is that your scripts will have command line arguments. So, and there's special variables that allow you to retrieve these. So for instance, if you write a script and you wanted to take command line arguments like this, then in that script you can access these with a $ and then the number. The first number, so $0, actually contains the name of the script itself. A $1 will be the first command line argument, $2 will be the second argument, and so on. And you can also get the list of all command line arguments as an array by $@ or $# to get the number of arguments. So that syntax was quite similar to the arrays that I showed at the beginning, just for the command line arguments. So now I want to show you a kind of a case study where we introduce all these, or where we actually use these concepts. So this is a real case problem that I faced one day. So, and I guide you how I solved it. So the problem that I was facing is I had written this Pulse application. It was a simulation model, and it took a few arguments. So it took 2 command line arguments minus CMT, and I just hard-coded to Winslow Rice. It also took a case name. In this case, it was just called ellipsoid. And then as a standard input, it also took an input file. That input file contained all the configuration of that, how the simulation was supposed to be run. And then I use T to store the output to file, but also, so main output is the file name, but also to display it on screen. So, and of course, I mean, this is kind of the standard command, and I had put it in a shell script. And that is, everything is hard-coded, and that's worked perfectly fine because I just wanted to remember how to run the simulation. But of course, as soon as you want to do some more experiments, just hard-coding everything isn't so flexible. So then it's useful to improve that script. And so just kind of three main limitations that we have here is that the command line options are hard-coded, right? So Winslow, Rise, ellipsoid, ellipsoid.i, and main output, they're all hard-coded in my script right now. Another problem is that the output script, main output, is overwritten every single time I run my simulation. So I lose the outputs of previous simulations, which is not very useful. And then this ellipsoid.i can't really be controlled through my program. So it needs to be, it's kind of just a hard-coded file as well at the moment. So it would be nice to be able to generate a suitable ellipsoid.i file depending on command line arguments that I pass to my script. So kind of these are the three limitations that we want to address. And the first one is, how can we make the command line arguments more flexible? So one easy way is well, the first thing that we do is, instead of hard coding them in here, we introduce variables. Okay, so for the case name, the input file, but also the output file and the CMT here. And then we define the variables, and so some of them, right, it's fine to hard code them, but maybe one of them we want to get to the command line argument, and then what I do is I do a simple if test. So I check if the command line arguments is larger than 0. So here, this I actually know is an integer, the number of the length of an array, so I can do an integer comparison. And if I at least have one command line argument, then I set that variable to the option that was provided to the program, right? And otherwise I use the default value here. So that's good. At least if I only want to change a single parameter here, and if you want to change multiple at the same time, I'll show you how to do that in a second. So then the second problem is that every single time I run this program, I overwrite the output files. So a simple solution to that is to create a directory with a unique name and to store that file, to store the output in that directory. So the way I've done that, or one way you can do that, is you create a directory name that has this, that encodes the date and the time, the current date and time. So that's hopefully unique. So I use the date command here and store its output, and you use it to create a job directory. Then you use makedir to create the job directory, go into it, and then I can run my pulse up. And then also what's quite useful is I want to have a reference to always the latest simulation one that I created. So I use a link, which is, oh no, it's not shown here. Here we go. So then what I do is I go outside in my main directory again, and here I do an if statement, and I check if this directory L here exists. And so I do a link check. -L checks if a file name is a link. So if latest is a link, then I delete it, and then I create a link called latest that points to the job directory that I was just running. So the point then is that if I do cd latest, I will always get into the latest simulation one that I performed. So there's one more. It's a bunch of new commands here. Makedir creates a new directory. -l is a test against an if statements that you can use to check if a file is a link. And then ln is to create links. Oops. Okay. So here are some alternative options that you can use. So the problem with date is that it might potentially be that maybe you change the time format or something, and then you travel, and your computer changes the time and date, and suddenly you again have exactly the same directory name. So there's a few other options. You could use each process in Unix systems have a unique ID. So you could get that ID and create a unique name of a repository. So the $$ represents that ID. The problem is if you restart computer, the counting of processes starts from new. So that's not really unique. Then, of course, there's a special command that solves our problem straight away. It's called maketemp. Creates a temporary file in that case with a unique name, so that we could use. But we could also check if the directory exists. And if it does exist, then we just exit with an error message. It just is safety handling. So the way you check if a file name or a directory does exist, you do an if statement and use the -d, and then the name of the directory that you want to check. So I have that simple if statement, and if it does exist, then I output an error message, and I exit the script with exit. And otherwise, I continue as before. So the last problem, there was this input file, ellipsoid.i, that I couldn't really change from the script. So it would be useful to take some additional input arguments and generate the input file on the fly. So that's the idea. So how do we do that? You can use the cat command. So the cat command, normally, if you write cat and then a file name, it just prints the content of that file to screen. But you can also use it to generate files, so especially multi-line files. So if you use cat and you redirect the output to your file name, and then whatever comes in here, this is the multi-line text that you want your file to have. And the nice thing is, so you need to have a stopping word, a starting word, and a stop. So here you specify a stopping word. So as soon as this word here shows up, the content of the file ends. So everything in here will be part of that file. And the nice thing is that you can also do a variable substitution within that command. So this is how you can create documents on the fly. Then we need to so now we want to extend our program to take multiple command line arguments. So of course we could have done, as I shown before, for a single command line, we just did a simple if statements. You could extend that and have kind of a list of if statements, but that's not very flexible. So a much better way is to do a while loop and loop through all the command line arguments that you have. And the idea is very simple. You check if the number of command line arguments is larger than 0. If it's larger than 0, you check what the value of that command line argument is, and then you remove it from the list of command line arguments. So you eat it away. So there's this command shift, and that simply removes the first command line argument from the argument list. So you have one less. So the logic here is the following. So we loop over the command lines. We get the option. We remove that option from the list, and then we check what options we are talking about. And I use a case. The case syntax here. So essentially, I'm checking in which command line option it is. So option could be either -m or -b or anything else. If it's -m, then I set a variable m equals the value of the second command line, of the first command line argument, and also remove that. Right? So the idea is you can write my script -m12 -b 18. So then m would be 12, and then b would be 18. And then in the other case, if you provide -x or something else, then you just put an error message and exit. So this is a structure that you will find quite often in shell scripts for handling these command line arguments. As I mentioned before, in principle, you can also do the same thing with if statements like shown here. Okay, so now we can put these two things together. So in order to create these config files, I use the cut command, and the configuration file, the input file, is also defined through a variable here. And then I simply specify all the parameters that I want to have in the config file. Some of them might be hard-coded, but other ones might be taken from the command line arguments that I've just programmed. And then I can run, so that previous command generated the input file, and so now I can just run my PulseApp providing that input file that I generated. So something that is quite important, or that is quite useful, is another special variable called $?, and that one, that variable either has the value 0 and 1, depending on the previous, if the previous command was executed successfully or not. So imagine the PulseApp that I just had. If I want to check if the simulation runs successfully or not, I can do an if statement like this. So I check if the $? is 0. If it's 0, it's successful. If it's not 0, then I can put an error message saying running PulseApp failed. And I can also exit the script with a non-zero exit code. So essentially, exit 1 sets the $? To 1 in that case and exits the scripts. So if my script was used in another script, that other script could also do error handling. So then sometimes you have the case that you want to extend your script that it handles multiple inputs at the same time. So for instance, and you don't know exactly how many inputs you will have. So let's say you have this run.sh script that is supposed to run my simulation for many different input files. So I could either just specify 4 different ones, or I could even just write run.sh star.i, which that means run it for any .i file that I have in my directory. So how would you handle something like this? You can simply use a for loop. So you can loop through all the entries in your command line argument and store the current value as arg. And then you just call pulse arg and arg is input. That simply loops through all the command line arguments that you provided. So this is also quite useful for file management. So for instance, if you have a lot of temporary files and you want to remove them, so if you wanted to kind of write a script to do that is like the following. You first use so this single semicolon is the same as running the command and storing the output. It's just a different syntax. So I run the ls start.temp file command. It lists all the temporary files. I store the result as an array called files. And then I use a for loop to loop through every single file, print in some text message, and then remove it. Okay, here's I'm not sure if I have time for this. I think I do. So this is, we managed this in 3 minutes. This is kind of a fun example to see what you can do with your Bash knowledge now. So your task is to write a script that it's called bundle, and it takes a bunch of files, and it's supposed to create an output and that bundles all these files together. It's essentially it zips it together to one file. So you can redirect that to a file called one file. But the trick is that this one file should be a Bash script that if you run it, it should unzip all the files again. Right? It should be a self-extractable zipper, so to speak, that we want to code up. Okay, so how do we do that? We have all the tools that we need. Just to give you another example. So let's say we have two files. File 1 contains, so this is suppose how it's going to work, right? So if we want to have a file 1 that contains these 2 lines and file 2 that contains some numbers here. So the idea now is that if we run bundle file 1 and file 2, we want to have a Bash script that that generates these 2 files again. And the Bash script could look like this, right? First echo unpacking file 1, and then we use our cat command that we've learned before to generate files. So cat store the following multi-line text into file 1, and then the content of the first file. And then we have another echo command unpacking file 2. And then we have another cat command which stores into file 2, and there we have our numbers. So our bundle script, the task is now that it should generate these types of scripts. And, oh no, where is it? Oh no, has it disappeared? I'm sorry, I might not be able to show you the solution. Oof. Oh, it's here. The solution is here. The solution is here. So what do? We loop through all the input files. Okay, 30 seconds. We loop through all the input files that the user provides, right, with a for loop. Then we call echo, but everything we echo is going to be Bash command. So echo unpacking file $1. Then, that's the file name. Then we do another echo, and the echo here will now be the cat larger the file name, and then smaller end of file. Then we output the content of the ith file, and then we finish off with the end of file statement to tell the cat command that it's finished, right? So I mean, it's essentially just echoing the right command so that you get a self-extracting Bash script. Okay, sorry, that was a bit. We do have some topics. I think I'm going to catch up next week with that. But that's it for today. Thanks.